My name is Taylor Zuccaro, and this is my 3.6 Math 251 project, Derivatives as Rate of Change using Calculus and Physics. The problem we were presented with was, suppose you leave school, which is 5 miles from home. You are confused since you just finished taking your calculus test, and you bike in the opposite direction from home for a while. Later, you turn around and head home again, but since you're so dehydrated and confused, you end up getting turned around again a short time later. Let S of t be your distance in miles away from home and at time t, which is hours. So our initial equation is here. S of t equals t to the third minus 8t squared plus 16t plus 5. And this is the position function. So the position function shows motion over a period of time. Here. Find and interpret S of O and S of 5. Show these values on the graph. So first, what I did was I plugged in 0 to the given position function, and I received the output of 5. And so since 0 was put in and we received 5 as our output, 5 was the distance, 5 miles. And when we incorporated S of 5 into the function, the output was 10 miles. And so here you can see that on the graph. Here's when we incorporated 0 into the function. And here's when we incorporated 5 into the function. In order to find the maximum and minimum distances from home and when they occurred, I first took the derivative of the initial function, and then from there I factored the function 3t squared minus 16t plus 16. I factored that to 3t minus 4 and t minus 4. I then set each of these equations to 0 and received the outputs for 3t minus 4. The output was 4/3. T equals 4/3. And then for t minus 4 equals 0, I received the output t equals 4. And these are in hours. So on the graph here, we have our maximum here and our minimum here. The minimum is 4,5 and the maximum is 4/3, 391 over 27. And as a decimal, that is 1.3, 14.5-ish. It then asked me overall what time intervals were you moving toward home, away from home, and show these intervals on the graph. So what I've done here is in different colors I have noted these intervals. Okay, so moving toward home, we have the green highlight here, and then moving away from home, we have this pinkish highlight. So moving toward home was between 4/3 and 4, so you can see here. And then moving away from home was between 0 and 4/3 until you reach here, and then the slope starts to go down. And then 4, 4 and 5, which we see here. So this is our initial descent from school in the wrong direction. This is when we realize we've got turned around and head back toward the right direction. And then this is when we are dehydrated and once again get turned around. That's what the graph is showing. It then asks to use derivative rules to find the velocity function, which I've already done prior in the beginning. However, we'll do it again here. So we have our initial function, which is the position function. And so what we're going to do is with the first one, we are going to move the 3 to the beginning, which I have done down here. Move the 3 to the beginning to get 3t, and then take that number that we did have there, 3, and that'll be our n minus 1, so then we're left with a 2 up top. And then minus here, we had 8t squared, right? So we move the 2 to the front. And so 8 times 2 is 16. That gets outputted down here. And then it was t squared, so then the 2 is the n minus 1, which leaves us with 1, so it's just the 1t there. And then we had the 16t, which there's an invisible 1. We would move to the front and multiply by 16 to get the output of 16. And then t is 1 minus 1, so we would get a cancellation of that t variable, and it would simply become 16. So our resulted derivative would be 3t squared minus 16t plus 16. From there, we are asked to graph that velocity function, and we are left with a graph that looks something like this. All right. And then we are to find and interpret v of 1 and v3 and show these points on the graph and explain what the function value means. So when we incorporate v of 1 into that velocity function, our output is 3 miles. So you can see I notated that here. And then when we incorporate three into the velocity function, our output is negative 5 miles, which you can see I've notated here. And the reason we're getting negative outputs for this is because the velocity function shows direction. So this direction will be the is this part of the graph where it's negative here is a turnaround point, a change of direction. So I put it in green because I put the green as good for on the right track back home. So initially it starts out, we're going the wrong way. And then we turn around. Sometimes a turnaround could be a bad thing, but in this case it's a good thing. And so it's negative now. That is a change of direction. But then we get turned around again, back in the direction we were initially going, which brings us back up to the positive. And the units of this graph would be in miles per hour because we were given miles at the beginning and our time interval of hours at the beginning. So number 3, use the derivative rules to find the acceleration function. So this is going to be the second derivative of the initial position function, or the derivative of the velocity function. And so in order to do that, we would apply the same rules we did with the last one. And here we would take the 2, multiply it by the 3 to obtain a 6. 2 minus 1 is 1, so we would just bring the t down. And then minus 16t, 1 minus 1 cancels it out. So the 16 drops down, and this constant gets eliminated. So now we have s of t equals 6t minus 16. Okay, so lastly, we're going to put all of these functions onto a singular graph and then go over what these all mean together. So here we have all of the functions on the graph. Here in green, we have our initial position function. Here in pink, we have our velocity function. And here we have our acceleration function. So this position function here shows the motion over a period of time. So it doesn't fall into negatives at all because it does not show direction. See how it stays up here? However, our velocity function does show direction. That's when it falls down here. And for our acceleration function, from here to here is negative area. And so that's when it has a negative slope or a change in direction. And that acceleration function is actually the slope or the rate of change of velocity. So that is the correlation between all three of those graphs. Then we were asked to locate the zeros or horizontal intercepts of each function and point at each one and describe them. So for our first initial position function, we actually do not have a horizontal intercept there because, again, it's not showing us the change of direction. And then, so for the velocity graph, however, when we do equal it to 0, we get t equals 4 hours and t equals 4 over 3 hours, or 1.3-ish. And the velocity graph reveals the speed of an object, whether it's slowing down or not. So it does reveal the speed, but it also here has the change of direction, that same interval that we saw in the position function when we get turned around. And the zeros at the acceleration function are at about 2.66. That is here. Okay. And that is when, again, we see a change of direction, or in this case, we see the negative area beginning here. So although we have a positive acceleration, we did have a change of direction here, which led to negative area. And that is the entirety of my project. So thank you so much. Have a good day. Bye.